Dr. Basu, my very distinguished colleagues, a large number of friends I have here, scientists of BARC, ladies and gentlemen. I am very happy to be here this morning to give a talk. I have come in spite of whatever I was doing, mainly because of the high esteem I have for BARC and atomic energy as a patron of science. Atomic Energy Department should never forget that they are the biggest patrons of science, and they have to protect science, and they are the champions of science. Because some of the best institutions of science in India are under atomic energy. Other than BARC, there are many, including the Tata Institute of Fundamental Research, all come under atomic energy, and it is with great respect and also adoration I have for this great organization created by one of our great Indians. I have come here. I am very happy to be here. I thank Dr. Basu and Dr. Sinha and all others for this kindness they have shown me. I am going to talk about science. You know, science to me is a necessary thing that man does. It is the result of a creative urge of man. It has nothing to do with grants, money. It has nothing to do with any particular external influence. It is the urge of man. Urge of man to create poetry, urge of man to create theatre, urge of man to create new societies, urge of man to create new knowledge. Science is one of those. It can never be suppressed. So the only thing one can do is to encourage. Only thing one can do is to promote it. And it is this science I am going to talk about. In that I am going to say much more on chemical science. I put in parenthesis because what I say also applies to all of science. There is a tremendous past, and the future, of course, is extremely challenging. 2011 is something that is very relevant to atomic energy. Before that, of course, we had 2009, 2008, we had two great celebrations. 200th anniversary of Charles Darwin, 150th anniversary of J.C. Bose, the first modern scientist of India. First modern scientist J.C. Bose, 150th anniversary of a man who brought physics to India. Nobody else had done physics of that kind. Unfortunately, he was cheated out of a Nobel Prize. He should have got a Nobel Prize. He would have been the first Nobel laureate of India for reasons now very well recognized. If you see the notes of the Royal Society, I have read it so many times that people completely acknowledge that without his work in Calcutta, there was no way Marconi could have discovered what he did. And unfortunately, being Indian, being citizens of colonial India at that time, we Indians were ignored at that time. Even nowadays we are ignored, but not as bad as those days. But J.C. Bose last time. Leaving that aside, 2011 is something very, very important for atomic energy. The centenary of the discovery of the atomic structure by Rutherford. Unfortunately, it amazed me. What amazes me is nobody celebrated it. No one in the world had a celebration for atomic structure. But as Feynman, the great physicist, said, if by some catastrophe the entire world is destroyed, one truth will remain, that is, all things in the world are made of atoms. And that atom, that structure was determined in Rutherford in exactly 1911. I want you to see the picture. I just intentionally showed this Rutherford with Cockcroft and Walton, the first Van de Graaff generation that were created in Cambridge, and this is Rutherford. And this atomic structure of Rutherford, of course, is wrong, slightly wrong, we know that. But even now, if you ask somebody what is atomic structure, what we show you first is the Rutherford atom. Other things come later. I just want to remind you of the famous Rutherford experiment. And for those who have forgotten, this is where the story of chemistry comes. Rutherford was a physicist. Like all physicists, had a slightly benign outlook for chemists. Chemists means the physicists think they are really brainy. But it's not true. It's not true. Actually, they think they are. But the real problem is they always had a very, very patronizing attitude to chemists. And Rutherford used to say, well, chemistry is nothing but collecting stamps. But you know what happened? After all this, when he got his first Nobel Prize in 1908, he got it in chemistry, not in physics. So that is an amazing thing. So it's one of the Nobel laureates in chemistry for having worked on disintegration elements. Again, there's a story of Rutherford. Many children here, I hope you don't mind, I call you children. All young people are children to me now. So our young students, I want you to remember, Rutherford went to Cambridge in 1895. 1895, till then, Cambridge University, where I'm still a professor, it never allowed any foreign student or anybody. You have to get a PhD in Cambridge, you must have an undergraduate work there. Otherwise, you could not do PhD in Cambridge. For the first time, they changed the rule in 1895. The first foreign student they allowed was Rutherford. And when he went there, the electron was just being discovered. Don't forget, electron was discovered by J.J. Thomson in 1897. And there he entered the lab of J.J. Thomson. Electron is being discovered, and the atmosphere propelled this young boy from New Zealand to do many things. Of course, imagine 1897, exactly 11 years later, he had a Nobel Prize. It is amazing. He was the emperor of physics. He was the greatest nuclear physicist, atomic physicist the world has created. No doubt about that. Why is that? Every body that we saw, he would bring them to the laboratory and they would end up with a Nobel Prize. Chadwick was running around somewhere, brought him, discovered the neutron. Blackhead, the discovery of positron, Cockcroft and Walton, then Kapitsa, the low temperature physics, the first low temperature physics in Cambridge. Of course, he also got a Nobel Prize. So the joke at that time, in Rutherford time was, people would say, if you please take me to Cavendish Laboratory, the Rutherford was, people, the taximan would say, no, I won't do that, because if I go there, he will make me do something and get me a Nobel Prize. So the taximan wouldn't go there. There was a joke about Rutherford. So Rutherford was one of the greatest minds I'm trying to remind you in the history of science. And of course, 2011 was also a centenary of another great thing, where atomic energy is interested, the discovery of superconductivity. In exactly 1911, superconductivity was discovered by Camerling Owens. This is this liquid helium liquefier. And you know, there is the next picture of Camerling Owens with his guru, Van der Waals. I just want you all know Van der Waals, and I just wanted to see pictures to get close to the great minds that we have in science. And this is also centenary we celebrated. Nobody celebrated it. It was there in 2011. Of course, this is the first superconducting transition of mercury reported by Camerling Owens. Well, 2011 is also a centenary of one more thing, because very important for atomic energy, because the entire area of atomic energy, all modern physics we talk about, started with the first Solvay conference historically. In fact, when I used to teach in IIT Kanpur, I used to give this picture to my tutorial class. I didn't ask them to identify each face in that. Because every brilliant scientist of that time was invited to the Solvay conference. I hope you can see Madame Curie here. There is, you see, Rutherford, Max Planck, and there is Einstein. You see, Einstein is standing there because he's still not so important. Einstein, you know, in 1911, he had still not become very famous. He was still doing things, you know, it is only after 1915 he became famous. Of course, this fifth Solvay conference, you see, Einstein is in the center. At this time, the name and what is interesting, you know, here in the atomic physics and nuclear physics, those of us do, there is of course Madame Curie, most important here, Niels Bohr. Niels Bohr, behind him there is a young man, the other part there, young man, that is Heisenberg. You see, Heisenberg was a project assistant under Niels Bohr. I hope you all know that. At the age of 22, he went and he wanted to work with Niels Bohr. And Niels Bohr went away on a holiday. You know, in Europe, everybody goes away for a month, usually in August and 2-3 weeks actually. Niels Bohr goes away for 2-3 weeks. And when he comes back, this young boy tells him, "Sir, I've made a very major discovery." "What is that? Let me see that." "Well, you know, unfortunately, I've already sent it for a publication in a journal." And then, you know, you couldn't wait for 3 weeks. I will come back. Yeah, but I thought it was so important, I didn't want to wait for anyone. So, you know, that is the one famous discovery for which he got a Nobel Prize. A few years later, the discovery of the uncertainty principle by Heisenberg. And these are all the big names, great names you'll see in this picture. I will not describe the picture much more. Well, we had a centenary of the Solvay conference in 2011. In fact, I was one of the speakers. For some reason, though I'm a chemist, they invited me. I had gone there. It was a fantastic experience to be amongst all these physicists. I was one of the few chemists there. But it was a very amazing conference. Well, 2011 is more well known because of the second Nobel Prize, celebrating this second Nobel Prize of Madame Curie. She got the second Nobel Prize in 1911, and again related to what you do in atomic energy, and she had discovered radium and polonium. And you see, this was celebrated as the International Year of Chemistry, as you know, and of course, that's very important. Of course, 2012, amazing, we have gone through centenaries of the greatest discoveries man has made in the last 3-4 years. So 2012 is a very important. You say, look at this young boy, 22-year-old boy, walking around the camp in the backs of Cambridge colleges. In 1912, he discovered X-ray crystallography. I hope some of you have read that paper in Nature, the structure of zinc sulfide by it's on my table even now, because I tell my students, can you redo that for today? It's amazing how he solved the structure by using X-ray crystallography. The first structural solution done in the history of science, and he was only 22 years old again. I guess 22 is a wonderful age. Heisenberg was 22, he was 22. And of course, much later he shared a Nobel Prize with his father, but the youngest Nobel Prize winner was 25 years old again when he got his Nobel Prize. And the reason I'm showing this is, there are more Nobel Prizes given in crystallography, use of crystallography, than any other subject. Whether it is protein, whether it is organic compound, inorganic compound, innumerable prizes have used crystallography, and that was of course just discovered in 1912. We celebrated the, and this year has been declared as the year of crystallography internationally, 1 year, 2 years late, but anyway, I just want to remind you that. Well, we celebrated the International Year of Chemistry in 2011, but I'm not going to talk about that. I'm going to talk a little bit about chemistry. Well, people say, of course, I'm told Dr. Sinha will tell you, where even today, even in India of the modern days, or even in Europe of the modern days, politicians have a tendency to ask scientists, why is science so important? Why should we support it? It's very common. Even today, amazingly, in fact, I was meeting my friend with the advisor to British government. He was telling me, amazing. Even today, the Prime Minister said, well, what is all this for? Why do you want all this? Of course, we have a tendency, even scientists do that. They don't understand the power of science, how science is required for the future. Without the foundation of science, there will be no engineering, no technology, nothing. Engineering itself is a science. Don't forget. Engineering is not technology. Engineering and science are very similar subjects. They are same. In fact, the best engineering sometimes is done by scientists, and best science sometimes is done by engineers. In fact, in some of the areas I work in, some of the greatest names are engineers who have done very good science. This is something we should not forget in a place like that. The reason I am telling you is, the answer is, just go 100 years back. For example, 2011, for some reason as an example, because it was the International Year of Chemistry, go 100 years ago, just technology had been discovered, radioactivity had just been discovered, noble gases had just been known, atomic structure just had come. So the condition 100 years ago, there was nothing called DNA, nobody knew any of these things that we talk about today. So the progress made by scientists is extraordinary in century. So I would like to spend a few minutes on chemistry, the story of chemistry. We consider Lavoisier as the father of chemistry. He died in the year 1794. He actually didn't die. His head was guillotined. You remember, there was the French Revolution in 1794. And Lavoisier was a very close friend of the king and the queen, Marie Antoinette, Louis XVI, and so on. And when the king and queen, their heads were guillotined, his head also was guillotined. They didn't realize what a great head he had, actually. It is a tremendous chemist. The reason we call him father of chemistry is, till the 18th century, chemistry as a subject didn't exist. If somebody asks what is chemistry, there is no chemistry. There is physics, natural philosophy, but Newton had established the foundations of physics in the 17th century. If you remember, in the 17th century, Newton had done all the wonderful things in physics, but chemistry was unknown until Lavoisier. So, since I'm giving a talk on chemistry, please remember, it is only towards the end of the 18th century, chemistry got defined as a subject. The reason he is called the father of chemistry, because he is the one who gave the idea of conservation of mass, very fundamental. He is the one who told what a compound has a finite composition. Air is oxygen and nitrogen. You are the one who showed it. Extraordinary man, Lavoisier. And of course, I want to see his picture. Always, it is that head that got cut off during the French Revolution. Because I always take a lot of pride, being, coming from Bangalore, and also I am very proud to be an Indian. I always will remember 1794 to 1798. I hope you all know this story. History of independence of India. You all know only after the annexation of Awadh, that is the first movement, 1857. Actually, in 1794, Tipu Sultan was fighting the British like mad right near Mysore, Srirangapatnam. He had defeated British twice. 1794 was one of them. He defeated the second battle of Mysore. Unfortunately, 1797 they came with so many guns and all kinds of things. He lost the battle. And that was a very bad period. That's exactly the time Lavoisier's head was getting cut off there in France. So 1794, 90 is a very important history. French Revolution, the British taking over India. If Tipu Sultan had defeated them in the third battle, there would be no British in India. Okay. Well, coming back to chemistry, again coming to atoms, the first recognition of atoms is Dalton's atomic theory. Every child in every school, even today, answers that question. What are the postulates of Dalton? Of course, when I was in school also, I used to be asked, what are the postulates? Even now I'm told they ask that question. And this is Dalton, a teacher of chemistry. And of course, I'm now coming to 19th century, 1867, and the greatest scientist of all time. This is something young people don't know that, particularly young people. People ask me, if you want to pick one name in science, which is that name? Well, then to me there is no question, it has to be Faraday. Nobody can beat his record. He might single-handedly, this man wrote 450 papers. There was no PhD student, no postdoctoral, no research grant, nothing. One man sitting and working and writing papers. It's amazing. How did he do that? He had only 3 years of schooling, but don't forget, he had no college education or anything. And he worked as an assistant to a bookbinder, and accidentally he attends the lectures of Sir Humphrey Davy on chemistry. And after attending the lectures, he writes down the lectures of Davy and binds it as a book and goes back to Sir Humphrey Davy. Sir, here is your 3 lectures by Humphrey Davy. I bound it as a book. Davy says, it's wonderful. If you do, thank you very much. He sends him away. Before going, Faraday says, do you think you can give me a job here? Like, as usual, all the administrators, there is no vacancy, I'm sorry. They send him away. Fortunately, 1 month later, Sir Humphrey Davy's lab had an assistant, a man who was cleaning things in the lab, who runs away, and he remembers Faraday and gives back, calls him this young boy, Faraday, and gives him the job. And his title in Davy's lab is unbelievable. Chief Bottle Washer of the laboratory. That was Faraday's first job. And then he started working with Davy, learning to do experiments. Eventually, he published the first paper in 1816. 1816, then only 25-year-old Faraday wrote his first paper without any school education. And went on doing better and better experiments. In fact, excelled his own guru, Sir Humphrey Davy. Of course, Humphrey Davy was a great man. He had discovered sodium. He had discovered so many major things in chemistry. And of course, I always show this one. The reason is, Rutherford was asked, if Faraday, unfortunately, was in 19th century, there was no Nobel Prize. Nobel Prize started in 1901. If only he were in 20th century, Rutherford said, he would have got at least 5 Nobel Prizes. Well, I have counted, many of my friends well known for the history of Faraday have quoted 4 definitely he would have got. 5 I'm not sure. Look at this. Last electronics would have got a Nobel Prize. It take the fact that not catalysis or discovery. He was the one who discovered benzene, most important organic compound. So that he would have got a Nobel Prize. And more than that, he discovered a lot of things in magnetism. The word paramagnetism, diamagnetism, permittivity, electrode, ion, cation, anion, all the words you use every day are all coined by Faraday. And of course, probably some of it would have got more than anything. He discovered electricity, very, very important. Of course, this famous story, I'm sure even today we can give such answers to our many administrators and politicians. When he discovered, one of the questions was, what is the use of this discovery? The famous answer, what is the use of a newly born child? That is the famous answer. But more important was the finance minister, or Chidambaram, equivalent of our Chidambaram in Delhi, the head of the finance ministry in England came and asked Faraday, what is the use of your discovery? He told him, look here sir, someday you will tax it, he told him. And then he discovered electricity. And this was Faraday. That was very, very fantastic. It is very pertinent to what we people do here. Someday they will tax what we are doing, but while doing it, nobody understands the importance. That is the thing about science. Science is like that. And Faraday's discovery, electricity went to, but he was also a very wonderful man. You know, as a human, it was very important to me. The greater you become in science, simpler you should be in life. Simplicity and greatness must go together. If as a human being you are not a simple person, I don't see what the greatness alone is not enough. Faraday was a very simple man. For example, you know, he was given a knighthood by Queen Victoria. And he wrote back, my dear Queen, thank you so much for this great honor by making me a knight. And I'll be hereafter called Sir Michael Faraday. But you know, everyone calls me Michael Faraday and all that. I don't want the knighthood. I hope you don't mind. He doesn't accept the knighthood. He was like that. And then I remember I've been a fellow of the Royal Society for 35 years now. Even today, being an FRS is not easy. He was an FRS, of course. Even though he had 3 years of schooling, he was an FRS. And then, you know, the Royal Society writes to him, dear Mr. Faraday, we would like you to become president of the Royal Society. Great honor in England at that time. But he said, no, my place is in the laboratory. Please excuse me. You know, nowadays I find people want to become director, then director general, then something else. They're always looking for bigger. You know, I don't know why. I think to be a scientist alone is important. No, he was like that. He was a scientist to the core. He never accepted the presidentship of the Royal Society. To me, in my life, if I were to admire, adore, and worship one scientist, I would only pick Faraday as an example. And of course, I mentioned this Mendeleev, you all know he is a crazy Russian scientist and Indian scientists are very similar. So both don't get recognition. Mendeleev, you know, he is very interesting. But Russians, you know, you may not know many things for which Nobel Prizes have been given later had already been done in Russia. There are many examples. Mendeleev is a very curious story. You know, this is a lesson to all the young people who want to get Nobel Prize, okay? Mendeleev in 1906, I have seen the original documents in the Nobel Committee. The Nobel Committee decided the prize for 1906 must go to Mendeleev for a periodic table. And just when it was about to be announced, the day before or 2 days before, the French people come and ask him, you know, there is this guy, Moissan, who has just put the element fluorine. You know, he's not very well, he's going to die very soon. Why don't you give him this Nobel Prize this year? Next year you can give it to Mendeleev. Then what happens? They give it to Moissan for 1906, Moissan dies after that. And poor man, this man lived till 1907, he couldn't get it, he died before that. So one of the major important advice to young people, live as long as possible. Okay. You know, this is another thing. There are some people who have become very patriotic. The patriotism comes out in the worst possible way. For example, they say, in India we knew everything in science even 5,000 years ago. Well, we used to do this, but we didn't know what was what. There's a problem. We didn't know it. See, first century, human beings knew only 7 elements. 16th century, 10 elements. I'm sorry, this should be 23. Lavoisier's time, we knew 23 elements. Lavoisier's table of elements at 23. Today, of course, 117th element is also being talked about. Well-defined 114th element. Because I'm showing my guru, Glenn Seaborg, a very great man who made a very important element. I hope you all know in atomic energy what element he made. He made plutonium. I think very, very important for all of us here. So, because of this, I can say, chemistry is not, though we say it is 200 years old, started in the 18th century, for all practical purposes in the 20th century, because all the elements we know only in the 20th century. Okay? And this is the periodic table. And I gave a lecture in Sweden on some occasion last year, and I did say that the greatest table man ever made is this table. I don't think there is any table with more content in it, more information, knowledge, and futuristic uses This is the great table, periodic table, for which the man who started it didn't get a Nobel Prize. Okay? Well, I just like to remind you, the first compound on earth was made by Wohler in 1828. Since then, there is urea. Since then, many compounds have been made. This is Wohler in 1828 who made the first compound. Then many compounds have been made. I just show one photograph of one scientist, Woodward, many others. Organic chemists have made all kinds of compounds. But it was very important at one time, but unfortunately, synthesis has now become quite routine. It's no longer as highly valued as they used to be in my younger days. But anyway, these are all the great synthetic people who did a lot in chemistry. Well, as far as I'm concerned, modern chemistry, the way I understand today, started really when we decided to put 2 electrons between 2 atoms, call it a chemical bond. This, of course, is due to J.N. Lewis, who wrote the first paper on chemical bond in 1916. Unfortunately, very few chemists, very few scientists have read that paper. This is a great pity. Everyone should read how this man sitting alone in the lab thought of a chemical bond, wrote the first paper, 1916. Much later that Linus Pauling took it on himself and gave a greater description of the chemical bond of Lewis. The same idea of Lewis, but he gave a better theoretical basis for that. And this is G.N. Lewis. I show him with a cigar because he always smoked a cigar. When he was alive till 1946, people who knew where the chemistry department was in Berkeley because they could smell it from a distance. And they just thought, oh, go to that thing, smell of the cigar. Because one of the greatest minds we have had in chemistry. Unfortunately, he is not a person who has not been, who never got a Nobel Prize. I will talk about it in a minute. And this is Linus Pauling when he started working the chemical bond with the young wife. In the young Linus Pauling. You see, always old people's pictures are shown inside. You know, young crazy man with a grey hair comes like that. Oh, Einstein does. So it's not like that. Linus Pauling was very young and handsome with a young wife when he started working on the chemical plant. What did Lewis do? Again, being in atomic energy in laboratory here, I want you to remember that. Remember one other thing. The first idea of the chemical bond. The idea of activity, fugacity, a lot of things in thermodynamics. But the first one to bring thermodynamics to chemistry. First book on thermodynamics in chemistry. Idea of a chemical bond I already mentioned. Then the electrochemistry, ionic strength, a whole bunch of things like that. They were the first ones to idea of Lewis acids and Lewis bases. My guru, Glenn Seaborg's PhD thesis under Lewis was Lewis acids and Lewis bases actually. Got his PhD under him. And you know, the Nobel Committee, he was nominated 15 times for chemical bond. The Nobel Committee then said, I don't think chemical bond is such an important thing in chemistry. Amazing, amazing, this is exactly what they said. And later when he discovered Lewis acids, it's not very clear Lewis acids and Lewis bases would be accepted in chemistry. Every time, he was nominated 23 times, he didn't get it. In the end, a story goes for atomic energy again. You know, his student, in fact, all his students, Glenn Seaborg got a Nobel Prize, Joe got for adiabatic demagnetization, Melvin Calvin got for photosynthesis, so many. And then he had Harold Urey. Harold Urey was one of his students, he got his PhD under him. Harold Urey discovered deuterium, I hope you all know, in Columbia University. And when he was coming, I've been told by my guru in Berkeley, who was Lewis' student, and he used to say, hey Harold, what is this deuterium you have discovered? What is the use of this element? Unless you make a compound, it is no use. But then he is the one who first made heavy water in the lab and started distributing it. In fact, James Wood sent small ampules of D2O to anyone in the world who wanted to work on it. He published 23 papers. Please see the literature, Journal of American Physiology, on the thermodynamics of heavy water, what happens to chemical bonds, hydrogen bonds, when you, in protein, when you, the amount of spectroscopy, fantastic. But in the end, Nobel Prize was announced, only Harold Urey, no Lewis. It is a shame, the Nobel Committee can make very bad mistakes. It is one of those great things. Lewis, to me, is the greatest brain of chemistry of the 20th century. I would put Linus Pauling below him, certainly not above, not even equal. I just want to show that he died. Would you mind if I take a couple of more minutes? You know, there's a story I want to tell young people. You know, I like to tell stories in chemistry. In 1946, he had a friend, he was doing something in the lab. he had a student, not friend, who is a very great friend of mine, who just died, Michael Kasha. Kasha's spectroscopy work, many of you know. Kasha and I were very, very good friends, much older than me, 8-10 years older than me. But Kasha was his last PhD student. He tells Kasha, I want you to run this spectrum in a high direct concentrate solvent. What solvent? Liquid HCN, liquid hydrocyanuric acid. You know, Kasha said, no, how can HCN liquid, I won't make it. I'm sorry, it's very poisonous. He said, you go to have lunch and come back, I will make it for you. It was a great experiment, J.N. Lewis. When he came back from the lab, lunch, there was in a tube on a vacuum line, liquid HCN. And then the laboratory was stinking of bitter almonds. I hope you all know HCN smells of bitter almonds. Don't try to find out. I'm just saying, believe me. And then, there was Lewis sitting on a chair. He had died. The question is, did Lewis commit suicide or he just died by accident because of HCN? Nobody knows even today. And my guru, with whom I work, was a great scientist there, who was Louis. I used to ask him, he used to be the dean of chemistry when I was there in the 50s in Berkeley. I used to ask him, how did he die? J.N. Lewis was such a brilliant man. He would look, even a suicide looked like an accident. And he is one of those. And unfortunately, that day, one story is there that the day that he committed suicide or died, Langmuir was visiting the laboratory. Langmuir and he hated each other. Langmuir got a Nobel Prize, of course, for surface chemistry. One of the things of cheating on science, let me tell you, is a very interesting case. It's not cheating. Mild cheating. Cheating is too strong a word. It's very difficult to say. Langmuir, even today in textbooks, they will say, octet theory of Langmuir, they will say, for chemical bonding. But Langmuir didn't discover that. Lewis had already written papers on octet. Except he didn't call it octet. He talked about the 8 electrons. And Lewis became so angry at Langmuir, he wrote to Journal of American Chemical Society editor, how can you publish this? This I've already written that long ago and everything. He just called it octet, so it becomes Langmuir theory. So in the end, Langmuir apologizes to him. He says, I will never publish any more papers on that. And JSCS also acknowledges the original author was Lewis. But unfortunately, even today in textbook, Langmuir octet theory is still there in many Indian books I see. But that day, I believe, the story goes, Langmuir was visiting to give a seminar in Berkeley. And he saw him at lunch somewhere. Maybe he got all worked up because Langmuir by that time had got a Nobel Prize. Well, I'm telling you a human story. A great man, probably the greatest mind we had in chemistry in the 20th century. He had a death or maybe suicide, whatever, under most unusual circumstances. Why do you think I think he's great? He asked him, what is interesting? What is science? But instead of that, they said, what is chemistry? What is physical chemistry? Nothing. Chemistry, physical chemistry is nothing that is, anything that is exciting, that is chemistry. Anything that is interesting, that is physical chemistry. So that is the definition of science. You do something that is exciting, don't call it physics, chemistry, it is good science. Do that, that's something exciting. That is why I like Lewis, he is my academic grandfather. The person with whom I did my postdoc was his student. Well, Linus Pauling is also my grandfather because, I will tell you later, I got my PhD with Linus Pauling's student. So they have two wonderful grandfathers, J.N. Lewis and Linus Pauling, academically. Well, chemistry, once chemical bond became important because of Lewis and Linus Pauling, it was dominated. In fact, I am a child of that period, 1950s. In fact, I will never forget, I was a student in Benares. I went there in 1951. I used to read journals, people who talk about bonding, quantum mechanics was just coming, spectroscopy was just coming, but nothing of that was being done in India. That is when we realized right away that I must leave India, somehow to get a PhD somewhere else, mainly because of that. But chemistry was dominated by molecular structure until about 1970. Reaction mechanism, new methods of determining structure, spectroscopy, and so on. But in this, I must mention, in 1951, again, this is where I was in Benares doing my BMSc. I was exactly 17 years old at that time. Linus Pauling reported the alpha helix. In fact, I got so excited. I asked my teacher, what is this protein alpha? Nobody knew. Amazing, the knowledge of science and chemistry in India at that time, less said the better. Nobody said, well, I didn't know. So I immediately wrote a letter to Linus Pauling by hand. Dear Professor Pauling, you have done an amazing, great discovery. Can I come and work with you for PhD? He wrote back saying, well, I wrote, unfortunately, without knowing, can I work with you on structure and molecule? Because I had read his book on nature of the chemical bond. He said, no, I no longer work on molecule. Why don't you work with my student who does a lot of molecular structure by electron diffraction? I didn't understand anything. I did work with students, that's different. But this is the beginning of molecular biology. You see, chemistry is the foundation of biology. Unfortunately, we chemists were foolish enough to let biologists become independent. Molecular biology would have been one of the branches of chemistry, see? And even today, if you want to be a good biologist, better know good chemistry. Otherwise, there are a lot of second-rate biologists. We have many of them around in India. And same people who advance materials work on without knowing chemistry. So they're second-rate material scientists. If you want to know very good material scientists, you must know good chemistry. In the old days, some metal alloy, melting something, not anymore. Those days are gone. Chemistry has become a foundation science, a fundamental science, and necessary science. Not even necessary, essential. If you don't know good chemistry, you don't do good biology most of the time. That started with Linus Pauling. And this is the picture of Linus Pauling when he did the discovery. See, now older, you see. That earlier picture was when he started chemical bond. This is when he discovered the structure of Linus Pauling. This is the Pauling I remember when I met him in 1954 in America. I had by that time discovered two structures of Linus Pauling by diffraction and methylazide and carbon suboxide, I remember. You see his third edition of the Nature of the Chemical Bond. Both my structures are included in this book. And that was the great Linus Pauling. Well, when I was in IIT Kanpur, in 1960s, we would say chemistry was nothing but structure, synthesis and dynamics. And this was in fact true. But unfortunately, that stayed for a very short time because of the tremendous input of biology to chemistry, advanced materials to chemistry. Today, the two main streams of chemistry are in biology and advanced materials. Other things you can do, publish papers, but we want to be the mainstream chemistry. Well, I'll skip that. Well, I'm trying to remind you, high temperature superconductivity when it came in December 86. You remember the first liquid nitrogen superconductor made was YBI2CU3O7, a so-called 1,2,3 compound. This is what we made in Bangalore in March 1987, 90 degrees transition. The reason I'm showing this is, this was the important hallmark for chemistry. There is a wonderful report of the US National Academy of Science where it says, chemistry got recognized by people in material science and physics of materials in general because of their contribution to making these superconductors. Till then they thought, well, at least they go on doing something. But this made them, all the important superconducting materials were made by chemists, so that gave them importance. Well, then fullerenes came, again discovered by chemists, C60, C70, carbon nanotubes came, various things that came out of chemistry. But chemistry has again changed. See, they didn't think about science. I'm sorry, I spoke in Hindi. Turn it off. The molecules, Hindi comes naturally to me, and that as if it's my first language. I don't know why, but both my wife and I have that problem. Molecules were important till about 70, till about 80. Suddenly, what has happened today? Molecule, structure, synthesis, well, it's okay. If you go to Cambridge University, or Harvard or Berkeley, where I go, I'm still a professor in California, not even one professor in chemical synthesis anymore. Things have changed. People work on self-assembly, supramolecular things. This is the report of the National Academy of Science. Very important report. I urge everyone to read it. It is called Beyond the Molecular Frontier. Chemistry is beyond the molecular frontier. And various important chemists work on living systems, therapies, optimization in biological systems, new synthesis, completely new substances, self-assembly, complex chemistry. I mean by complex chemistry, chemistry of the earth, sea and the atmosphere, materials by design, of course computation. I don't want to mention, you all know it, but today people can compute as well as you can do the experiment. In fact, computer simulation, computer calculations today are so good that in fact we have to verify that by experiment. Well, one or two words. Energy. People ask me, what is it that work on in atomic energy? I don't have to tell you this. I think energy is and will be an important thing. India has two major problems. I hope you all have thought of it. Water will be one of the biggest problems of India. Unfortunately, we have done nothing about water. Management of water is worse. Agricultural water, rain water, anything. Water goes, flows, nobody saves, everything is unbelievable. And the rainwater wasted in Bombay alone is enough for 3 months of Bombay supply. That's what I read somewhere, maybe not 3 months, maybe 2 months. But still, it is unbelievable. So, but unfortunately, they are not working on these problems. For example, I have not mentioned in chemical approaches, hydrogen storage, generation, hydrogen energy, solar energy, of course, fuel cells, batteries. But solar, of course, is getting too much mention. It is true, solar heating we can do. See, solar photovoltaics is important, but the target India has a maximum 20,000 megawatts. Alright, maybe 30,000 megawatts. Still a very less than 10% of our rings. It's not going to solve our problem. We need problems to be solved in such a way that our cars and our planes and trucks can be run. For that, of course, we need fuel cells, batteries, maybe supercapacitors, hydrogen, and of course here I use the word, I only show one example. I'm not talking about my research, so I thought 2 minutes of my research I should show in a talk. So artificial photosynthesis. Artificial, by the way, about hydrogen, I want to see, in 1874, there's a very nice book by Jules Verne, the famous Jules Verne, I hope you all know, Around the World in 80 Days. And what will they burn instead of coal, asked Pencroft. Water, replied Hardin. But water decomposed its primitive elements, yes my friends, I believe that water will one day be employed as fuel. That hydrogen and oxygen which constitute it will furnish an inexhaustible source of heat and life. Water will be the coal of the future. It is written so long ago, there's absolute truth in that. And then what is interesting is, many of you know that because I found that you people are interested in water splitting, also by thermal means. Of course, I am very much interested in semiconductor nanostructures. I just show you one. You all know natural photosynthesis. In photosynthesis, you do oxidation of water and reduction of water. Oxidation of water to give oxygen, and even reducing proton to get hydrogen. Hydrogen, of course, is in plants that is used to make food, but we don't want that, we want to get hydrogen. Oxygen, of course, comes out because of the reaction of the holes that are created in the process. For example, this is what happens in natural photosynthesis. When the electron gets excited from CH1 to CH star, of course, then it picks up, loses an electron, then the reduction occurs to give food, and it forms a positive ion. But you can't keep that positive, it needs an electron. So the so-called water oxidation complex, for which the structure of which was solved by Barber in Imperial College a few years ago, that gives the electron. Well, that cannot be charged, it has to become an electron, that electron comes from water, and that water goes to proton. You wonder how plants will do such a complex thing. You can't do it in a beaker and a flask of the reactor. But you can, using semiconductor structures. And in fact, this is the structure of the water oxidation complex that James Barber found in a peculiar core of this kind. And what we do in the lab, in my lab, is to take ruthenium, excite it, and then of course we go to ruthenium-3, and of course that electron is used for some reduction process, any inorganic or organic. I normally use this or benzyl alcohol or something going to some other thing. This is one of the places we can use electrons. And then this catalyst, instead of using the water oxidation complex that nature has, I use a catalyst of mine. And then of course that picks up an electron water and water gets oxidized. And in fact what we have just now found is the best catalysts are oxides of cobalt and manganese. And unfortunately there are 3 communication JSCS last 3 years, all of them are wrong. They are from Princeton. They said you need a cubane structure because the so-called water oxidation complex looks like a cubane. It's not true. What you require is cobalt or manganese in the oxidation state 3 with 1 electron in the Eg orbital. LSO3 is T2G5 Eg1. That's why you see LaCO3 is one of the best catalysts. With the high turnover factor, Mn2O3, you see these are all the manganese oxides, orthorhombic manganese oxides, all very, very good, but the best is the LaCO3. Manganese oxides are T2G, 3Eg1, all that you need at 1 Eg electron. T2G, 5 Eg1 there. Of course, we make hexagonal magnet are useless because you no longer have an octahedral manganese with Eg1 electron. Well, we have a paper in Proceed National Academy of Science last year and many other things coming out. Another thing we are doing is semiconductors for water splitting. I hope you all know this band diagram. You need a material whose conduction band is more negative than the reduction potential of protons, and a valence band that is more positive than the oxidation potential of water. And so you see, the best zinc oxide is not bad. CDS is not bad. But molybdenum sulfide, look at that, perfect fit. Well, we have done a lot of these things. I will not talk about that. Except molybdenum sulfide, H2 generation. And what we do is a dye-sensitized thing. You take molybdenum sulfide here in a metallic form. You can create 1T MOS2 by lithium intercalation and exfoliation. You take the dye, excite it, you go to triplet state, then an amine picks up an electron from an amine and becomes negatively charged. That negative charge, the electron is transferred to this MOS2, then proton gets reduced to hydrogen. And we have got very, very high 55 moles, even 70 moles in one cases, millimoles per gram per hydrogen, excellent hydrogen. And you will see that I can show a demonstration model, just put a tungsten lamp, hydrogen keeps coming out like mad. And they have and many other things coming out in these things. Lastly, a semiconductor nanostructures were made. Take a zinc oxide nanoparticles on which I put platinum nanoparticles and then cadmium sulfide nanoparticles. I use the holes to oxidize benzaldehyde, and then proton reduction is done at this end. And we have got 50% the apparent quantum yield is very, very high, much better than what Ari Santosh from Berkeley has given using this kind of catalyst. And recently, zinc oxide is useless in the visible region because it's colorless. We have made zinc oxide and we have able to color by doping zinc oxide with nitrogen and fluorine. Zinc oxide has a color of orange color. Now this kind of a material gives visible light induced hydrogen production fairly high, number of millimoles, 50, 60, 17. In this, it's about 35. We have done this kind of work. So this is one of the areas of work where 2 or 3 of my students are working. Now I would like to close my lecture by making some general comments. What did we do yesterday? The reason I am saying is that is life of science. There is no day which is a holiday. 7 days a week is full day, working days, to me at least. If there are 6 days, Sunday afternoon we can take off. And that's what it is. You can read newspaper on Sunday afternoon. But 6 days, yeah. I think wonderful life I've had personally doing science in this way. The reason, one of the reasons we have not been able to work probably in India as much compared to China is Chinese are very, very hardworking. Of course, they have got a person with a whip all the time, so they are very afraid, I guess. We don't have whip there in India. We are very nice bosses here. People are very kind. So we also work less. Well, we are not a hardworking nation. There is no doubt about that. Well, when I call myself working, my students are very easygoing. I mean, they come at 10 o'clock, 9:30. I get up at 4:30 in the morning, waiting for my students all the time. I don't mind. Young people can have a good life, it's fine. But what is interesting is, chemistry or science demands all the attention. When I sleep, when I eat, when I go around, so the undercurrent is something that is very me. Well, I'm very me. I compose paragraphs and sentences when I'm breathing, when I'm talking. Because what is the best sentence I put in an abstract of a major paper I'm writing? I worry a lot. And people say, oh, how come you publish 1,500 papers? Well, because I'm working very hard for 60 years. You have to do that. I've had 25 students. Don't forget, each one paper, that's all you get. You get 25 papers. And you have to work very hard. More than working hard, it is tremendous undercurrent of science that really dominates you. And that's why when somebody says, what did you do yesterday? Well, there's no yesterday. Yesterday, tomorrow are all the same. And then we should also not forget the history of science. You see, the reason we lose respect for our own profession is because we are the carriers, we are the bearers of the great traditions of science. We are carrying the tradition of Rutherford, Chadwick in this laboratory here. They are the people who created nuclear physics, the great spectroscopists, great chemists, Lavoisier onwards in chemistry. And we cannot forget that. But I will never forget I am the grandson of Linus Pauling. But that didn't mean biologically has nothing to do with it. But certainly, academically, J.N. Lewis, my grandfather. In fact, the man with whom I did my MSc thesis, S.S. Joshi in Benares, my MSc thesis, he worked with John Donnan membrane equilibrium. And Donnan worked with Ostwald. So Ostwald is my great-grandfather. The reason I talk with my father and grandfather is not because of anything else. The spirit of continuity of science is should not be forgotten. You must not forget the stories of science, stories of scientists, how they looked, how they did, how they thought of things, how did Faraday do all this thing, how did Ramanujan, with nothing at all, no scholarship, no money, how did he write 3,000 theorems sitting in the miserable hole in South India? Awful place. How did he do that? Not because somebody gave money and throw things at him. Faraday also, nothing, nobody gave him anything. So this is the one that attracts me to science. That extraordinary demand on you from a source that is not known. That tremendous thing. It's why people ask, you are going to be 80 years old, how come you are still working like a young boy? I tell you, it is really so. Kabir Das, we all know Hindi. Kabir Das, I hope you all know the famous thing. Man mein Ganga, man mein Kashi, मन में ध्यान करो, मन में स्फूर्ति, मन में आसक्ति, मन में ज्ञान, सब मन से, मन में that man we have to create. In India somehow we are not doing that. We have to create that for science. I am sure under the leadership of Sinha and Basu, BARC will be a center like that, where each one is bubbling with enthusiasm, trying to do new things beyond the working hours, beyond the holidays, beyond everything, because they are excited, they want to solve a major problem. To me, science is that, and I have enjoyed this science. I have worked 63 years now in research, of which 55 years I have been a professor. Been a wonderful life. More than anything, you must believe me, I have never uttered a lie in my life. Unpleasant things I will tell you, pleasant things also I will tell you, but if people don't like it, it's unfortunate, because I don't have time to lie. To utter a lie, you need a lot of energy. To achieve somebody, even more energy. Best is to say everything and just do your work. And very important, therefore, honesty, integrity, and selflessness. And this helps. In fact, I tried my best to help as many people as possible, as many people as possible. You can't help everybody, and as many as you can. But the selflessness is very important in science. Unless we in India have generosity, allow the young people to come up, India will not do it. In fact, selflessness is something the great Rabindranath Tagore, in his Gitanjali, in his 30th poem, he says, the selfishness, self is the one that follows you everywhere. He says, I come out alone on my way to my tryst, but who is this that follows me in the silent dark? I move aside to avoid his presence, but I escape him not. He makes the dust rise from the earth with his swagger. He adds his loud voice to every word that I utter. He is my own little self, my Lord. He knows no shame. But I am ashamed to come to thy door in his company. That's why he talks about selfishness. I think science is the most selfless profession. And teaching is similarly so. But I have been blessed with this profession. I am very grateful. I am very grateful for this poor country. It was very poor. You won't know how poor. We could get $5 when I started my career in 1959. $5 was a big amount in India. It is impossible to get $5. In fact, all my research was done by taking empty suitcases all over the world, fill it up with all kinds of white and black powders and wires and thermocouples, come back. All my research was done by them. And you people at that time, BARC was more endowed, we had more facilities here, more equipment, but we came from poverty. But I am grateful. I am grateful for everything. But the only problem in India is, we have no time. We have lost the value of time in India. Look at the way TV programs, disgusting. We have all the time in the world for this. India is burning. We have to do something. If we don't do something in India in 10 years, maybe 15 years, maybe 20 years, not more than that. You know, China, South Korea, everybody is coming up. We will be way behind. Not only in army, something like that, economy, in science. I want only science, I'm the only worried about science. We have to be as good as the best. How do we do that? We'll have to do something about that. And so, I think we should do science because we love it. We should do science because we think that is the foundation of everything. Without that, there is no technology, nothing. As when I was in Korea recently to give a lecture, the Swedish Academy, Nobel Committee had arranged a symposium in South Korea. I was one of the speakers. When I was there, the president of South Korea announced, I am going to give $50 billion for the next 5 years for fundamental research in South Korea so that the long-term future of South Korea is safe. I want such a statement to be done in India by somebody. Because that's for the future. I want that to happen. And you know, and for that there is very little time. You know, time to me is a very, very precious thing. I hope if you don't know, I'll read out a very important thing about time that Michael Faraday said. One of his friends complained to Michael Faraday, you know, I've not heard from you, you've not written to me. Michael Faraday wrote back, I'm sorry, I have no time. Do you know what is the longest and the shortest thing in the world? The swiftest and the most slow, the most divisible and the most extended, the least valued and the most regretted, without which nothing can be done, and which devours all that is small and gives life and spirit to everything. It is what the Creator thought was so valuable, He gave only a limited amount. If God thought, or Creator thought, time was easy, He would have made you live for 500 years. He said, no, ek saw se zyada nahi de. He said, come on, ek saw mein nahi milta. So I think time is very important, but India should realize that we have no time to fool around. And I think we have to do something. And I would like to close as far as I am concerned. I will always remember another poem of Gitanjali, where Rabindranath Tagore writes which poem, I don't remember the number. He says, you know, time has come, I become old, I have to say goodbye. I have to close the doors of my house, I have locked it, given away the keys. But you know, before I go, let me tell you something. This world has given me so much. I give it so little to the world. I feel exactly like that about science. Honestly, science has given me more than I have given science. There is no question about it. There has been a life which is so wonderful. And then of course I was there, those of you who love music, I'm a big music lover. The other day, accidentally my wife showed me a wonderful statement by Ustad Bismillah Khan. He used to play Shana in the banks of Ganges where I studied once. I still go there. Bismillah Khan, I'm sorry, what do you want? And I went to Hindi again. He says, oh God, oh Almighty, as long as I live, let me live in the world of music. That's all he prayed for. It's a wonderful prayer. Thank you so much.
Actually, I have lost my words after such a lecture. Thank you very much, sir, once again. Now I request Dr. R.K. Sinha, Chairman Atomic Energy Commission, to give a memento for visiting us and talking to us, to our chief guest, Professor CNR Rao. Now I request Garat, who has made a special memento for Professor CNR Rao. Sir, this will be kept in BARC.
Honorable Bharatratna Prof CNR Rao, respected Dr. R.K. Sinha, Chairman Atomic Energy Commission and Secretary to the Government of India, Dr. Shekhar Basu, Director BARC, Dr. K.L. Ramkumar, Dr. Jagtap, and many invited dignitaries who have been also our mentors. I can see Dr. Kapoor, Professor Joshi, Dr. Grover, Dr. Sangs, Dr. Sood, who has been my mentor all along, Dr. Mittal, Sri Bhardwaj, Dr. Venugopal. Hello colleagues, ladies and gentlemen. It's my pleasure to have been asked to propose a vote of thanks on this National Technology Day celebration. It's a great honor, rather a big opportunity for me especially to thank Bharatratna Prof CNR Rao for having accepted our invitation to grace this occasion and to share his views in this intimate gathering of scientific community. Sir, jewel in the scientific community and obviously the role model scientist for all of us. It was so nice to hear you that you called us children, and that is what it is. And especially for our younger generation to emulate. Your words of wisdom during the interaction with the young scientists has infused enthusiasm and spirit. Your excellent talk, rather it is so excellent, has inspired and motivated all of us. Sir, we are all exhilarated to your great words. Thank you for this gratitude. We also express our sincere thanks to our beloved chairman, Dr. R.K. Sinha, who has been a constant source of encouragement. Dr. Shekhar Basu, Director BARC, has taken keen interest and practically guided this program. A big thank you for this dedicated involvement. An event like this cannot happen overnight. The wheels start rolling weeks ago. I wish to thank all the young scientists and engineers, backed by their teams of motivated and dedicated colleagues, for presenting a bird's eye view in the area of chemical sciences pursued at BARC. It is not an easy task to bring out diversion of their research activities on a common platform and in such a lucid manner what we saw down. Thank you, dear, for all these efforts. We also thank DAE Homi Bhabha Science and Technology Award winners 2012 for accepting our invitation to deliver talks on this occasion afternoon. I must mention our deep sense of appreciation to Scientific Information Resource Division for printing up posters, brochure and other sports. Further, we are grateful to BRC Culture Choir for rendering the songs so beautifully. I may like to express our sincere thanks to Controller BARC, LNC Section, BRC Security, the media, and many others for their services on this event. Finally, success of this event also goes to the rapt attention and involvement of this audience. Of course, after hearing Professor Rao, it was obvious that those who missed it missed a great thing. The audience gives an excitement, it arouses, and confidence it generates. I would once again thank all of you for being with us today morning. Thank you, sir.